A student who is currently studying from one of my courses, in particular one course on vibrations, a course which is related to some research that I have carried out in the past, and in particular during my PhD. So it has to do with engineering, but there is lots of interest in mathematics and physics as well. But anyway, apart from that, the theory is in my course, and it is not just standard theory. I've also shown some advanced theory related to some research topics. And as you can see, this email from the student, I'm not showing the name of the student here, but I want to show you exactly what he's asking and how it is related to my theory, or in particular to vibration theory. It is something that I have explained in a course, and it is written in my PhD dissertation and in other articles as well. But here, let's see something related to engineering and something related to the world of vibration tests. So this student tells me that he's attaching a file. So we have already had some conversation before this email, so I'm just showing this email itself, and I'm not going to show you the name of the student or other emails. This student is sharing some acceleration data in G, so G is just a measure of acceleration. And then you have a sampling frequency of 3120 hertz, or if you want 3.12 kilohertz. And then is sharing the lifetime of a component, which is 15,000 hours, and the slope of a polar curve, which is also known as the SN curve. This curve is important because it gives us some information regarding the behavior of the material, in particular the behavior due to fatigue, to the fatigue mechanism. And then the student is also asking me to make an instructional video, which is something that I'm doing now, explaining the procedure to generate a PSD profile, a power spectral density profile, starting from the information that is given me and also the data that is sharing. This data.txt that I've also opened here is sharing this data. So where I have basically two columns in this file, in this text file. The first column contains the vector related to time. So you can see that according to the sampling frequency of 3.12 kilohertz, I have basically a time vector. And then on the second column, I have the accelerations, the values of accelerations in G. And he's asking to generate a power spectral density profile starting from this data related to 32 hours with these 10 minutes of data. So 10 minutes is because this data here, I mean the time column goes from 0 to 601, so these are seconds, and 600 seconds are 10 minutes here, so 601 seconds are roughly 10 minutes. So what does it mean that I have to generate a PSD profile for 32 hours? It means that, so since he's telling us that the accelerations that he shared with us are related to measurements that lead a certain component to failure in 15,000 hours, well, we want to make some accelerated tests by using this power spectral density profile, but the profile must cause failure in around 32 hours. So that's why it's an accelerated test. I will not get into all the details. I've explained most of them in the course, and they are better sketched in the PhD dissertation and also in the references contained therein. Let me also tell you that most of the algorithms that I have produced are related to what you can already read in the literature. For example, there are these famous books, I mean famous in this sector, so in the vibration sector, in this vibration research area, where the books were written by this author, Christian Lalanne, French author, and he wrote 5 books related to vibration and on all the theory, and all the possible ways in which you can implement the algorithms. In particular, my research was based on the fourth and the fifth volume that you see here. When I carried out my research, my previous advisor shared these books with me so that I could read them, and I did. As you can see, they are quite expensive, so it's quite unfeasible to buy them all. But what I can tell you is basically that all the relevant information that I used during my PhD to carry out standard research, because I've also carried out non-standard research, meaning that I have created my own algorithms, in particular related to the generation of non-Gaussian profiles. This is another topic, so here I'm just referring to standard procedures that are already available in the literature. And I mean, most of the theory that you can see in vibration research is contained in these 5 volumes. Now I don't have the volumes anymore because I have finished my PhD and I'm not part of the University of Bologna anymore. I'm just listing them, I'm just showing you how to find some material, and there is also free material available online if you search for vibration articles, but now I don't have the time to go through all the literature and all the important articles in the literature. Now let me go to MATLAB. In particular, this is not really MATLAB, this is a GUI, graphical user interface, created with MATLAB, but this is not MATLAB dependent because it can run by itself without the use of MATLAB. I developed it during my PhD. And let me tell you that starting from this data that the student shared with me, I created this other file. So I skimmed some of the details that are not useful here. I deleted the first row, and then I also deleted the first column, so the one that contains information regarding time. I don't need that because I can just use the information regarding the sampling frequency. I know that these acceleration data are in G, and they were sampled with a certain sampling frequency that the student shared with me, in particular this 3.12 kilohertz. So that's just what I need. And this is quite a complicated GUI because it can do all sorts of stuff related to vibration. I'm not going into the details. We are just interested in the synthesis of a PSD, so in the power spectral density. So I have to click on this button to start to let another GUI appear. You can see it here. It is quite a complicated GUI. I will not get into all the details of this software, but let me tell you that here I have to change some parameters. In particular, the Euler curve will be 5, so here I'm changing this value, and this zeta here is the damping ratio related to the material that we want to test, and let's put 2%. Most of the time the damping ratio for mechanical components, they are quite small, between 1 and 5%, but it really depends on what you really need to test. Let me also change the input acceleration units. I will put G instead of meters per second squared. Then we have other parameters which are important only for the fatigue damage spectrum. So when we have a signal and we want to understand its quote-unquote damage potential, in engineering we calculate the so-called fatigue damage spectrum. This parameter here is not really important because it is important if you want to estimate the absolute value, let's say, of the fatigue damage spectrum. But when you want to compare just two fatigue damage spectra of two different signals, this value here is not important because it fixes the actual value of the fatigue damage, but the relative value between two fatigue damage spectra is not dependent on this parameter. So this is just some intuition. I will not get into all the details here. And also this parameter C here is related to the calculation of the fatigue damage spectrum. Whereas this delta F here is the resolution of the fatigue damage spectrum. The larger this value, the easier will be the computations, because you will have less computations to carry out. So the more computations, the lower this value. If we put 0.5, it will take some time to do the calculation. It can be done even with 0.5, but in order to speed things up a bit, let's put 1 hertz. So it means that, for example, if we have around 1500 values, so we can cover all the frequency range from 0 to 1500 hertz. Now, before starting the synthesis procedure, I have to set the test duration. The student asked me to generate a PSD for 32 hours. So here we need to set 32 hours, but we have to be careful because this test duration here is set in seconds. So 32 hours multiplied by 3600, which is basically the conversion from hours to seconds, gives us 115,200. So 115,000, and then we have 200, right? 200 seconds. So this will be a test of 32 hours. Now we can run this synthesis procedure. I will not get into all the details of this GUI, as I said earlier. It is quite complicated, but I will have to input my file .txt, which is the one that contains only the column of acceleration values. So I will input this file. You can see that the GUI asks me if I'm using a file with just one column or two columns, because sometimes I can directly input the two-column file, and in this case I have input just the one-column file, so I have to select this entry. And then if I have just the acceleration column, I also have to input the sampling frequency. And if you recall, the sampling frequency is 3.12 kilohertz, which means 3120 hertz. So I have to choose OK. And then this is some. Then I have a set of questions that appear. And in particular, they are not really useful in this case, because it's asking me if I want to extract one particular situation. And one particular situation simply means that I want to extract just one part of the signal. And in this case, I want to keep all the signal, so I will choose no. Now I can do a preliminary analysis of the signal. I can choose yes, and I can plot both the PSD and the time series itself. So you can see that I have this PSD, and the frequency range is roughly from 0 to 1500 hertz. And this is the shape, this is the form that the signal takes in the time domain. So these are just the acceleration values that you saw earlier, just graphically represented. So you have the acceleration in g in the y-axis, and whereas on the x-axis you have the time, and it is measured in seconds. So if you recall, we have just roughly 10 minutes of data, so we have roughly 600 seconds of signal here. And I can keep it open, but I want to keep moving on. So I don't want to filter the signal. So sometimes it is useful, especially if you just have a small frequency range and all the other frequencies are useless because they are small. In principle, I could filter the signal, because you can see here that this part is not really important. It does not really contain any meaningful energy beyond this frequency here that you can see. So it's roughly, all the energy of the signal is roughly contained between 0 and 1300 hertz, roughly. So, but in this case, I will keep that. So I will choose no. I don't want to modify the frequency resolution, and I don't want to modify the duration of the signal that will be synthesized. So I will enter here the smallest frequency, 0, and then I will enter the maximum frequency over which I will calculate the fatigue damage spectrum. So let's put roughly 1500. I will choose OK, and then I have to insert the expected life under the inserted load in hours. If you recall, in the email that I received, the lifetime of the component was 15,000 hours. So that's exactly what I need to insert here, 15,000 hours, because it means that under the signal that I have input, which was those 10 minutes of signals, the component in question will last approximately 15,000 hours. So that's what I will input. And now you can see that a calculation starts, and this calculation is related to the fatigue damage spectrum. The calculation of the fatigue damage spectrum is quite burdensome, especially if there are many if the data contains lots of points, and if the frequency resolution is small, and also if the frequency range is large, basically if the sampling frequency is large. And 3120 is quite large, so you can see that it takes some time to do this calculation. And I want to show you this because it's quite important. You can see yourself that it can take some time. And this is not even the longest, because sometimes it can even take hours if you want to do some more detailed analysis. So the calculation is reaching its final stages, as you can see here. And let me also tell you that I have developed some algorithms, which are not really standard algorithms because I have developed them in my PhD dissertation, which help speed up this algorithm a little bit. So in particular, this algorithm here, this calculation procedure is using the well-known rainflow counting method. And I have found a way to speed the rainflow counting method a little bit. So I have already made some work on this, and it's written in my PhD dissertation. But apart from that, now we are ready. In particular, you can see that the GUI asks me if I want to load another signal, and it's called another situation because it means that we are compounding a signal, so we can compound the signal by concatenating several signals, and in principle this can be done. The GUI allows you to do that, but in this case this was just one signal, so I have to choose no, and here it is. So you can see that the GUI has just synthesized the PSD. You can see that on the left graph, and I can open it in an independent window. So you can see that the synthesized PSD, which is the cyan one, and it's a little larger than the blue one, which this can be explained in several ways. In particular, there are several reasons behind the fact that the cyan one is larger. I will explain the simplest reasons shortly. For now, let me tell you that we have created the same damage, quote unquote, the same damage, which means the same fatigue damage spectrum as you can see here. The cyan one is the one associated to the synthesized signal, whereas the blue one, which is hidden by, behind the cyan one, is the one related to the reference signal, which was the one we input, and the reference signal was this blue one here. So you can see that logically I have represented the power spectral density of the reference signal in blue, and also the fatigue damage spectrum of the reference signal in blue as well. So you can see that the fatigue damage spectra are basically the same, whereas the PSD spectra, so the power spectral density, are different. This is due to the fact that the synthesized signal, according to the standard procedure, is a Gaussian signal. And you can see that the reference signal is not Gaussian, right? And the other reason is that this damage, the fatigue damage spectrum here that you see on the right, is reproduced by the synthesized signal in a shorter amount of time, because if you recall, we have to produce the same damage, so we have to lead to failure the component in a smaller amount of time, which is 32 hours, with respect to the 15,000 hours of the reference signal. But the other reason for why the power spectral density is high is, the power spectral density of the synthesized signal is a bit more intense, is due to the fact that the generated signal is Gaussian, whereas the reference signal is non-Gaussian. And in general, non-Gaussian signals are able to cause more damage than Gaussian signals. So take this with a pinch of salt, because I'm just saying things in a way that summarizes what I did during my research, and this is something that can vary, can change depending on the input signals that you have. But generally speaking, non-Gaussian signals are able to cause more damage than Gaussian signals, because you can see that these areas here where you have these large bursts cause the non-Gaussianity in the signal, because the kurtosis, for example, and other statistical parameters differ from those usually found in Gaussian signals. Now, I can show you that if I generate the time series starting from the cyan PSD, I have generated the time series, and in particular I can plot the signal. So you can see here that I have generated 100 seconds starting from the PSD. This is called the realization of 100 seconds duration. And this red signal was generated starting from the cyan PSD. And then you can see that there is another PSD which is in red. And this red PSD is basically the same as the cyan one. The only difference is that the cyan one is theoretical, whereas the red one is exact, because it was calculated after the signal was generated, but basically they are the same. And there is a small error here in the legend that I can correct, because you can see that the PSD time series here in the legend is blue, but actually it's the red one. And starting from the generated time signals, we can also calculate the fatigue damage spectrum. You can see that now. The cyan one is the theoretical one, but let's see if after the calculation we are able to see that the fatigue damage spectrum is exactly the same as the fatigue damage spectrum of the reference signal. So we have to compare the fatigue damage spectrum of the actual generated signal with the fatigue damage spectrum of the theoretical signal, which was the reference signal. And we will see it in a moment. It should appear in red, and here it is. So if I open it, you can see that yes, there is some calculation difference, because you can see that they are not exactly the same. The red one is not exactly the same as the cyan one, which has to do with the fact that there are algorithms which use some formulas, and the formulas are theoretical. So once you do the calculations by implementing the algorithms, there will be inevitably some differences between the theoretical calculations and the practical computations that are performed by a computer. But the results are quite good if you just check. So what I will do here, after showing you this short synthesis procedure, I will save the power spectral density that I have generated. I will save it to my desktop, and I will save the synthesized PSD, so the cyan curve. I will also save the frequency vector, and I will choose the file name, which will be just PSD synth, and I will choose it to be a text file, just like the file that I input to the GUI, but in principle you can save MATLAB files and Excel files as well. So I will choose text format. Let me also open it. Let me go to the desktop. I will open this file, and you can see that indeed we have the frequency vector on the left, so it's the first column, and then the second column are the values of the PSD, which are measured in g squared divided by hertz. So this is the unit by using g. It is also possible to convert g's to meters per second squared, and you have to check that this is g squared. So it's an energy which is the square of a signal. It is related to the square of a signal per unit frequency, so it's divided by hertz. So the integral of the PSD over a frequency range will give you the energy of the signal, roughly speaking. So I will share this text file with the student that contacted me. I cannot really share, unfortunately, the algorithm, so in particular I cannot share the GUI because this was developed while I was a PhD student, so this should be considered as property of the University of Bologna. And my project was funded also by another company, an external company, which you can see here on the bottom right. This company is a small company in Italy, especially, I mean, they work in Modena, and they also collaborate with important companies in Italy and with big names in the automobile sector. And I can mention a few. I can say for sure Ferrari, and also Lamborghini, and the other important one is definitely Maserati. And this company funded my project, and then we also worked together on synthesizing signals for other companies which had to do with the automobile sector, but also with the sectors that have nothing to do with automobiles. I'm thinking, for example, of companies that work with gears and transmission systems, but they still have to do with fatigue failure and vibration analysis. So we collaborated with them. So that's just a simple overview, but of course there would be more to it than meets the eye, because all the algorithms are they were implemented here, but they need to be implemented with caution, because sometimes the implementation of the algorithms itself requires some care, some attention. So especially during the implementation. One thing is the theoretical part, and the other thing is the implementation. It can be done exactly starting from the theory, but you have to be a little careful when you have to do the implementation. And the description of the algorithms can be found in my PhD and also in other articles in the literature. And as I said earlier, in these famous books written by Christian Lalanne, but there are also others. These are just all-encompassing books that contain lots of information. And that's it. I would say this was just an example. As I said, this is just the standard procedure. So we generated standard Gaussian signals, but it is also possible to carry out accelerated tests by using non-Gaussian signals. And this has to do more with my research. But so far, what I've shown in the video is not related to my research. It is not something that I found out in my research. It is something standard. After recording the video, I came up with one more point of attention. In particular, let me conclude by showing you another curve, which is called the MRS, which is short for maximum response spectrum. It is similar to the so-called ERS, the extreme response spectrum. So let's just think for a moment, and for simplicity, that they are the same thing. So basically the MRS is going to tell us the maxima of the responses of the single degree of freedom systems for each natural frequency. So for example, you have this peak here at around 340 hertz. So for each natural frequency of the system, you have a different response. And here on this graph, you see the maxima. So the blue curve is it represents the responses to the reference signal, whereas the red curve represents the responses to the synthesized signal. So the Gaussian signal is the red one, whereas the cyan one is the theoretical one, but let's keep that aside. You can see that the responses to the Gaussian signal are much larger than the responses to the non-Gaussian signals, to the reference signal. And you have to pay attention to this. This is due to the fact that we are accelerating our tests. So it makes sense that since we want to accelerate our tests, we want to make more damage in a shorter amount of time. The same amount of damage in a shorter amount of time. And this translates to having greater peaks in the responses, greater bursts in the response signals. But you have to be careful because we are carrying out fatigue tests. So if the response is too high here for the material, we might change the failure mechanism from fatigue failure to a yield type of failure, which is to be avoided if we are carrying out fatigue tests, because if we change the mechanism, then our tests would be pointless. They would have a different purpose. So we have to pay attention to this. We need to make sure that such peaks that we have in the response are not capable of breaking the component by yield type of failure. So we need to stay away from breaking the component due to these peaks. We have to break the component due to fatigue failure. That's a different story. This was just some kind of additional information that I wanted to add to the video.